Hello again. This video is going to start section 3 on exponential functions and their properties. But before we do that, I want to just wrap up or review domain from a formula a little bit more. So this is going to end section 2, which is domain from a formula. Just because I want you to have some more examples so that you can see what's being done there. So if we have f of x equals 5 over x minus 3, this is very similar to the one at the end of the previous video. So what we have to ask ourselves, again, we're asking for domain, so find the domain. That's the question, okay? And remember, your question for yourself about domain is, what am I allowed to plug in? Remember, that's the ultimate question when you're talking about domain. What are you allowed to plug in? Well, there are restrictions here of what you're allowed to plug in, because remember, this is a fraction. The denominator of a fraction is not allowed to be 0. Let's remind ourselves of that. The denominator of a fraction is not allowed to be 0. So what we need to ask ourselves, since it's all about what's being allowed, is we have to find out what value for x, or what value of x, will cause the denominator to equal 0. That winds up being the ultimate question. So look at how this progressed in our own minds. What am I allowed to plug in? The denominator of a fraction is not allowed to be 0. So what value of x causes the denominator to equal 0? Because that's what's going to be restricted. Well, if x minus 3 equals 0, that means that x is not allowed to be 3. Because if we want x minus 3, if we want to know when that equals 0, that's going to equal 0 when x equals 3. And so now we know that's a bad number. So the domain, you can simply write x can't equal 3. Or if you do prefer to write in words, you can say all real numbers, all real numbers except 3. So it could be anything else but 3. All right, and if we do one more, let's say we have the function f of x equals the square root of x, and same question, find the domain. Okay. We have to know a little bit about square roots, okay, and how they work. A square root is basically the reverse of squaring something. So we know that 2 squared equals 4. So the square root of 4 is 2, okay, because you're looking for that square, okay? What can you square to get you that number? So there's a problem, because negative numbers will never give you a square root. You can't take a square root of a negative number. So that's something that you need to be able to write out as a fact, okay? We can't take the square root of a negative number. And again, why is that? That's because you're looking for that same number to multiply with itself to get you what's under here, what's underneath, what's called the radical. Another name for the square root sign is a radical. And there's nothing that you can multiply with itself that's going to give you a negative number, okay? That doesn't work. So if x can't be negative, we basically just restricted the domain, okay? We just said x can't be negative, okay? So x can't be negative. But I don't want to phrase it as what it can't be. I want to phrase it in what it can be. So if it can't be negative, that means it can be 0 or anything positive. So that tells me that the domain will be all x greater than or equal to 0, for those of you who like the inequality notation. Or for those of you who prefer interval notation, x can be 0 and anything up to infinity. Okay, and this will eliminate any negative numbers. So these are the types of things you're looking for when you're being asked for a domain from a formula. So now let's move on to section 3, which is what this video is really going to be about. So this is section 3, which starts exponential functions. Now in class, I would like us to do an activity where we're exploring an exponential function and the power of exponentials. But this video is really just going to give you the background. So first, let's look at the graph of exponentials. An exponential function has a very distinct looking graph, okay? It comes hovering above the x-axis and then shoots up. That's one possibility. This is called exponential growth, or in other words, this is an increasing exponential. Okay, we know it's increasing because we read graphs the way we read, from left to right. So as I go from left to right, I'm going up the paper. Okay, but that's only one orientation. The other orientation for an exponential is to decrease. So it'll come down and then it will hover above the x-axis. So it'll sharply come down and then it will flatten out. And this is called exponential decay, or in other words, this is a decreasing exponential. Again, following from left to right, we're coming down the page, okay? So this is a decreasing exponential. And the good news is this is basically it, okay? This is what an exponential function will look like. There's a couple of facts, okay, about these graphs. First of all, you can see that they do have y-intercepts. Okay, but we talked about how this hovers, okay? This is never actually going to touch the x-axis. So one unique feature of an exponential function is that there are no x-intercepts. An exponential is not going to touch the x-axis. And that's something to observe, okay? So now let's talk about what it is that's creating this pattern, okay? Because you probably heard in the news a lot, especially with coronavirus, about exponential growth, okay? What does that mean, right? This is a real life concept. We're hearing it every day. So let's take a look at an example of a table, okay? So we have this function labeled x and f of x, our input, our output. And let's say these are our ordered pairs, 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, and 5, 32. And if I were to graph this, remember we're labeling first. Graphs always get labeled before you move on. I'm counting by ones for my input. That's pretty easy. But notice that I have to go all the way up to 32 for my output. So I'm not going to want to count by ones because it's going to take me a long time to get up to 32. So maybe I want to count by fours. Fours could work. Maybe I want to count by twos. That part's totally up to you. So we can actually let's see. We could do 4s. So we have 4, 8, 12, 16, 20, 24, 28, 32. Okay? And now we're going to plot these values. So we have 0, 1. We're going to have to approximate where 1 is. Okay? So right there, it's about 1 out of 4. Okay? We have to approximate that number. 1 is 2, right? That's about halfway between 0 and 4. 2 goes to 4. 3 goes to 8. 4 goes to 16. 5 goes to 32. And I can see that it is making this pattern, okay, an exponential growth. So I can connect the dots. Remember, when you see that pattern, you can connect the dots, okay? But now the question is, what caused this pattern? Okay, we care more about the why in mathematics. We don't just want to memorize things. We have to look for patterns. Mathematics is actually the study of patterns. So let's think about this. What caused this sharp increase, okay, to come on? If I look at this, I do notice that there's a pattern. If I multiply by 2, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, times 2 is 16, times 2 is 32, and I can see that that's what's establishing the pattern. So this is a very important fact to be able to pick out, because this is actually called the factor. Okay, factor is a very important vocabulary word for exponentials. I also like to call it the multiplier, because that's actually physically what you're doing. That is the multiplier of each consecutive output. So let's actually put that as a definition. This is what the output gets multiplied by for every 1 change in input. This part is key. You're not going to be able to identify a factor, at least at this level, okay, in this course, if you don't have a 1 change in input to start. So that's the first thing you really should be looking for, is if you have a 1 change in input, and then you look for this pattern. Is there a constant multiplier? Okay, so that's what we want to check for. Okay, this factor, you can also call it a constant multiplier, because it's always being multiplied by the same number as we go on in the table. Okay, now let's look at a different example and see if we can still spot this multiplier, because that was an increasing exponential, that was growth. Can we do one for decay? So let's do another function, x and f of x, and let's say that it's 0, 1, 2, 3, 4, 5 again. But our output is 64, 32, 16, 8, 4, 2. Okay? And first, let's make sure that this does, in fact, make the picture that we're thinking it's going to make. So we're going to label. We're going to make our tick marks, counting by 1s. It's the easy part for the x-axis. Let's take a look at what values for f of x might make sense as increments. 8s might actually work pretty nicely here, because I have to get up to 64. So let's do 8, 16, 24, 32, 40, 48, 56, need one more space here, 64. Okay, so we have 0, 64, and we can identify that as a y-intercept because x is 0, thinking about previous videos. Then we have 1, 32, Then we have 2, 16. Then we have 3, 8. Then we have 4, 4, which will be halfway. Then we have 5, 2. And we can see that that pattern is established. And again, it's never going to touch or cross the x-axis. It's going to hover like that. All right, so we can see that it follows the pattern of an exponential. But why? Okay, what is that multiplier? Well, can we see what's happening for every one change in input? Okay, as my input changes by 1, can I spot a pattern in my output? Well, this looks like it's being halved every time. So I'm timesing by 1/2, or in other words, dividing by 2. But because we called it a multiplier, I want us to continue with the idea of multiplication. So we're multiplying by 1/2, or 0.5. I multiply by 1/2 again, multiply by 1/2 again. Okay, so half of 32 is 16, half of 16 is 8. Okay, and all of these are multiplied by 1/2. That resulted in decay. Okay, very interesting. So when I multiplied by 2, I got growth. And when I multiplied by 1/2, I got decay. Let's think about that. Okay, if I multiply by a fraction, I will be getting smaller and smaller and smaller amounts every time. Okay, because I'm multiplying by a fraction. I'm only taking a part of what it was previously. When I multiply by a whole number, we all know how that works. That gets larger and larger and larger. So it makes sense that those kinds of factors, those kinds of multipliers, will result in that pattern. So that's a fact that we can now write out. If the factor is greater than 1, okay, so this is our greater than sign. If you are going to think that you're going to misread that, you can write it in words. If the factor is greater than 1, we have exponential growth, because we're multiplying and it's getting larger and larger and larger. If the factor is between 0 and 1, so the factor is stuck between 0 and 1, or in other words, the factor is a decimal or a fraction, okay? So we can put that in parentheses here. The factor is a decimal or fraction. So it's stuck between 0 and 1. We have exponential decay. And that, again, should make sense because we're taking part of what it previously was every time. So it's going to be decaying or decreasing. All right, so hopefully this helped you buy into what's causing this pattern, okay? What's making the exponential growth. But now, maybe we want to be able to figure out, without just spotting the pattern, how you actually calculate the factor, okay? Because maybe it's not going to be so obvious that it's exponential. You're going to need to be able to calculate the factor. This part is a little bit harder, okay? It does have to do with a formula. The formula for factor is the division of two consecutive outputs. So it's f of x plus 1 divided by f of, x. This does look very confusing because I'm using f of x's, okay, I have x plus 1 here. What does that mean? All this means is the division of two consecutive outputs, okay, when the x differs by 1, like we said before. That's all this means. Also, if you don't want to think about it like this, and you have available to you f of 1 and f of 0, so an input of 1 and an input of 0, and you can divide those outputs, you can just go for that, okay? So all this means is that the input is going to have a difference of 1, and you're going to divide those outputs. So let's put that in words. What we're really doing here is we divide outputs when the inputs have a difference of 1. That's really all this says. Okay, same thing that we said before and did before. Okay, we're just putting it into a formula. So let's do it as an example. Let's say we have x and f of x. We have 0, 1, 2, 3, 4, and we have 1, 2, 4, 8, 16. Now, I'm not using more sophisticated numbers here because I just want us to see that the formula works. Okay, so this is actually very similar to the one that we had before. I want to divide consecutive outputs. So the difference in my x's is 1, which is what's needed to be able to do this. And I'm going to divide f of 1 by f of 0. So I'm going to divide 2 by 1 because that's f of 1 divided by f of 0. And I get a multiplier of 2. Here's the thing. To determine if it's exponential, it has to be true the whole way down. So yes, you're going to have to do it the whole way down. So now I want to see what f of 2 divided by f of 1 is. Again, all I need is a difference of 1. So that means it's going to be the output 4 divided by 2, which is 2 again. Okay, that looks promising. Then I want to divide f of 3 by f of 2. That's going to be 8 divided by 4, which is also 2. And this is looking really good. When I divide all the consecutive outputs, I always get 2. So now I know that 2 is my multiplier, or in other words, my factor. So my factor is 2. So what does that mean? That means every output is doubled every time x goes up by 1. Now, a lot of people ask, well, why is it division? You're calling it a multiplier. Why are we dividing? Think about what the opposite of multiplication is. The multiplier here, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. It's obvious that as we go forward, we're multiplying by 2. The opposite of multiplication is division because I'm not going forward. I'm trying to figure out what I need to do going forward, which means I need the reverse. So instead of multiplying going forward, I have to divide going backwards. Okay? So it's just like you were reading this. 2 times 2 is 4, but 4 divided by 2 is 2. Okay? So it's going backwards to be able to determine what that multiplier is. Okay? Let's do one more using the formula for factor. Let's say we have x and f of x again. We have 0, 1, 2, 3, 4, 5. And we have the same one we did before, 64, 32, 16, 8, 4, 2. But this time, I'm not going to have the picture. I need to decide if it's exponential on my own. So the factor is f of x plus 1 divided by f of x, okay? All you need to know there is the division of consecutive outputs. So I want to take f of 1 divided by f of 0, which will be 32 over 64. You can do that in your calculator. That gives me 0.5 or 1/2, depending on if you want to leave it as a decimal or a fraction. F of 2 divided by f of 1. That's going to be 16 divided by 32. Calculator will tell me that's 0.5 or again, 1/2. Keep going down to check all of the divisions. This is going to be 8 divided by 16, which is 0.5. f of 4 divided by f of 3 is 4 divided by 8, which is 1/2, or 0.5. And then last but not least, f of 5 divided by f of 4 is 2 divided by 4, which is also 1/2, or 0.5. Okay? So the fact that this is constant the whole way down tells me that two things. It tells me it's exponential, and it tells me the factor is 0.5. Okay? So this is exponential because the output is constantly multiplied by 0.5 for every one change in x. We're actually going to put that in words. This is exponential because the output is constantly multiplied, because again, that's why it's called the multiplier, constantly multiplied by 0.5 for every one change in x. And that's going to be how you determine if you have exponential change. Okay, last but not least for this video, we're going to talk about the formula for exponentials. Exponentials go by a very specific formula, okay? The formula is going to look basically identical or similar for all exponentials. The formula for exponentials is f of x equals ab to the x, okay? You ever wondered why it's called an exponential? The variable is the exponent, okay? So the input is the exponent, hence the name exponential, okay? Turns out that these two values also take on very important roles, okay? They're very specific numbers. This b always turns out to be that multiplier. It's the factor. That's why the factor is going to turn out to be so important to figure out. And this a value is always going to be the y value of the y-intercept. Okay? And that's always going to be true as well. So let's take a look, just so you're not just buying what I'm saying. I want you to really believe what I'm saying. Let's say we have f of x equals 64 times 0.5 to the x. Okay? And let's do a quick table of values. Remember what a table is asking you to do. X is independent. These are your choice. I can pick -1, 0, 1, 2. Okay? Just like in previous videos. These are your choice. Okay? And then f of x, to fill in the column, you're just going to plug in whatever you decided over here. So this is going to be 64 times 0.5 to the -1. Put that in your calculator, okay? The way to do that in your calculator, by the way, 64 times 0.5, you want the caret button. That's your exponent key. Caret -1, okay? And that's going to give you what you want. So this is going to give me an output of 128. Then I do the same thing for 0. We're going to find out in the next chapter, anything to the 0 power is 1. So this is going to give us an output of 64. Then I put in 1. This is going to give me an output of 32. And then I plug in 2. And this is going to give me an output of 16. Now, I want to just prove to you what I said up here. Okay, I don't want you to just buy into what I said up here. I need you to actually believe it. Okay, I need you to see it. The factor needs to be that multiplier. If I take all of these sequential outputs and I divide 64 by 128, that's going to give me 0.5. 32 divided by 64, that's going to give me 0.5. 16 divided by 32, that's going to give me 0.5. So my factor is constant. Every output is being multiplied by 0.5 for every one change in x. 64 happens to be my y-intercept because the y-intercept occurs when x equals 0. So 64 happens to be my y-intercept. So now I know that just being given a formula, I can pick out the factor and I can pick out the y-intercept. The y-intercept here will be 0, 64. And don't forget to write that as an ordered pair, okay? That's going to be your ordered pair. Last but not least, okay, a very quick check to make sure that you're dividing the right way. This is a decreasing exponential. You can see that it's decreasing simply from the pattern in the table. A decreasing exponential should have a decimal factor, just like we discovered at the beginning, okay? If you divide the wrong way, that won't coincide and you know there's some sort of issue. You know there's a problem. So you can go back and try to figure out what that problem is. It's probably that you divided backwards, okay? When it is growth, you can spot the growth here just looking at the pattern. Your factor should be greater than 1. If your factor is not greater than 1, again, it's dividing backwards, okay? So that's a very quick and easy check to make sure that you are dividing the right way to get the wrong size factor or the right size factor, however you want to look at it. So I hope this makes sense. We're going to do a lot more with exponentials, okay? But if you have any questions, please let me know. I'll see you in the next video.